We take so many things for granted, like how a liquid dough turns into a solid cake. But behind even the simplest things lies the science of materials. So the real question is, can we live without understanding them? Hi, I'm Kate, a material MSE contributor and the founder of my own blog, FSM Materials. FSM Materials is a blog that helps everyday people understand material science around us. I've started it because I've always been fascinated with how material science can explain the why of our world, from food to aerospace and electronics. Baking is a great example of material science in action. Any baked good always starts with the same main ingredients, one of which is an egg. An egg is so essential due to its ability to bind other ingredients together, because without any eggs, a cake would simply fall apart. Zooming in, an egg is composed of the shell, the egg white, and the egg yolk. Proteins are a major constituent in both the egg white and the yolk. These proteins are a type of molecules that usually look like long folded chains. The chains are held together firmly, but by weak bonds. Now, let's imagine we've mixed our egg with our dough and put it in the oven. The heat that the oven supplies reaches those protein chains, breaking the bonds between the folds apart. This causes the protein molecules to unfold, in the process known as denaturation. Upon unfolding, the groups of molecules that have previously been buried within the protein become exposed to their surroundings. And there are two types of these groups, hydrophilic and hydrophobic. The hydrophilic ones are attracted to water, and so remain connected to water molecules in the dough. The hydrophobic ones, on the other hand, are repelled from water, and so they bind to other ingredients of the dough, like the molecules of air or flour. At the molecular scale, this turns the dough into a 3D mesh-like structure, and we get a solid, baked cake. The same principle can be applied to biodegradable packaging and even drug delivery systems, showing how material science can turn everyday chemistry into innovation. Material science also determines the prices of products. For instance, the price of diamonds can go up to as high as $5,000 per carat because of their extreme scarcity. But let's look at these stones up close. A diamond is made up of carbons and atoms, which are arranged in a structure called face-centered cubic lattice. Each carbon atom is strongly bonded to four other carbon atoms. This gives diamonds their hardness and transparency. However, this particular pattern of atoms can be created only under extremely high temperatures and pressures. The only place with these conditions on Earth is deep underground, some 150 to 200 kilometers beneath the Earth's surface. Though, as we have seen, origins of its stone matter, it is the processing that makes or breaks a diamond's appearance. When a diamond is first extracted from the ground, it looks very raw and cloudy. The stone is first analyzed for any impurities using modern technology. Then, the craftsman determines the best way to cut the stone, maximizing its symmetry, transparency, and size. This is the point at which any mistake would send the diamond's price flying down. This is a perfect example that in materials, structure determines properties, and even tiny atomic changes can decide the material's value or purpose. Material science does not end on a small scale. In 1986, the failure of a material led to the explosion of an entire space shuttle and deaths of the crew members. This was the 1986 Space Shuttle Challenger disaster. Being an NASA mission, the sole number of engineers who were involved on the project promised it to be a successful flight, so nobody expected that, 73 seconds after the launch, the Challenger's solid rocket boosters would explode and the shuttle itself would plunge into the Atlantic Ocean, killing all 7 astronauts on board. Turns out the problem lay in the material from which one of the components of the space shuttle was made of, rubber. Rubber as a material has properties change based on temperature. In hot temperatures, the molecular chains in rubber are free to move, making it flexible and elastic. However, below a certain temperature, the movement of the chains is restricted, and the rubber turns rigid and brittle. On the Challenger shuttle, rubber was used to make O-rings. These were placed in between fuel segments to ensure that hot gases didn't escape. The way that this system worked is that when the hot gases combusted, they exerted pressure that caused the fuel tank components to bend away and create an opening. However, the gases also raised the temperature, so the O-rings, becoming more flexible, expanded to fill the gap. However, on the day of the launch, the temperature unexpectedly dropped below 10 degrees Celsius, causing the O-rings to lose their elasticity and turn rigid. Therefore, when the hot gases combusted and the fuel tank components created an opening, the O-rings didn't expand to fill in the gap, and hot gases escaped and ignited the aircraft. This is a tragic example of how understanding material behavior, especially under extreme conditions, is critical to safety and engineering. From jewelry to spacecraft, materials shape every part of our lives. They can prevent disasters, create beauty, and drive innovation. The more we understand them, the more we realize material science isn't just about things, it's about possibilities. Thank you for watching, and I encourage you to read more about material science on fsmmaterials.com and materialmse.com.